Something has entered our solar system, and it doesn't act like it should. It arrived from interstellar space, traveling for billions of years before entering our neighborhood. Its orbit is hyperbolic, meaning it doesn't belong to the sun. It isn't gravitationally bound. It is a visitor, a traveler from another star system. It passed close to the sun and barely reacted. It moved past Earth, and now, as it nears Jupiter, the anomalies are increasing. A 620,000 kilometers anti-tail, almost twice the Earth-Moon distance. 3 perfectly symmetrical internal jets separated by 120 degrees. A rotation period between 7 and 16 hours. Oscillations like a lighthouse beam sweeping through space. A 16 degrees trajectory curvature near the sun. Large rocks being expelled. An unusual nickel-to-iron ratio. Organic compounds released only after perihelion. And then the nucleus. For concentric layers. One chaotic, one perfectly circular, one irregular like a fractured dome, and an inner layer showing near-geometric tagonal symmetry. Some scientists call it a rare CO2-rich interstellar comet. Others say the accumulated anomalies require deeper scrutiny because when symmetry, chemistry, trajectory shifts, and structural coherence all appear together in a single object, you don't ignore it. You investigate it. This is 3I/Atlas, and right now it has stopped the world. 3I/Atlas, officially cataloged as C/2025N1, Atlas, is the third confirmed interstellar object ever detected. Its hyperbolic trajectory confirms it has journeyed through interstellar space for billions of years before entering our system. After passing near the sun, it displayed minimal disruption and continued its path toward Jupiter. But recent observations revealed something extraordinary. A gigantic anti-tail measuring approximately 620,000 kilometers in length. That is nearly twice the distance between Earth and the Moon. This anti-tail was precisely measured using multiple major space observatories. It is not a subtle feature. It is colossal. Within this structure, 3 internal jets appear symmetrically separated by exactly 120 degrees. The object rotates with a period estimated between 7 and 16 hours, accompanied by a periodic oscillation of roughly 20 degrees. The configuration resembles a lighthouse beam rotating through the dark. Symmetry in cometary outgassing is not impossible, but symmetry this clean is rare. The dust being expelled consists of relatively large particles, forming an opaque reddish veil, seemingly regulating material release rather than dispersing randomly. Spectral analysis shows cyanogen, neutral nickel, organic compounds, and in certain phases a relative absence of iron. The jets are also aligned with the sun's rotational axis. That alignment is not trivial. It suggests structured geometry interacting with solar dynamics in a way that is not easily dismissed. As 3I/Atlas approached perihelion, its trajectory exhibited a curvature of approximately 16 degrees near the sun. That curvature coincided with the symmetrical orientation of the jets. Large rocks and extended gas were expelled during this phase, adding to the list of unusual behaviors. Then came another anomaly. After perihelion, after its closest approach to the sun, the object began releasing organic compounds that it had not previously emitted. This delayed release, combined with the geometric symmetry and compositional irregularities, produces a statistical profile that is difficult to explain through standard cometary sublimation alone. Before perihelion, volatile output was dominated by carbon dioxide with traces of carbon monoxide and nickel. After solar heating intensified, methane and additional organics appeared in significant proportions. Methane, being highly volatile, would normally be expected to escape early during heating, not remain concealed in deeper layers until later stages. That implies either internal stratification more complex than expected or mechanisms we do not yet understand. When you combine a 620,000 kilometers anti-tail, perfect 120 degrees jet symmetry, alignment with the solar rotational axis, a 16 degrees trajectory shift, large particle ejection, anomalous nickel-to-iron ratios, delayed organic release. You are no longer dealing with a single anomaly. You are dealing with convergence. And convergence is what forces the scientific community to pause. If the geometric anomalies raised eyebrows, the chemistry raised something far more serious. Questions about internal structure and origin. Before perihelion, approximately 87% of the volatile material being released from 3I/Atlas was dominated by carbon dioxide, with traces of carbon monoxide and nickel. That profile, while unusual in proportion, could still be interpreted within the broader spectrum of interstellar comet compositions. But everything changed after its closest approach to the Sun. Post-perihelion observations showed an intense surge in activity, stronger than expected, with substantial sublimation of water, carbon monoxide, and carbon dioxide. And then came the most debated signal. Methane appearing in proportions reaching nearly 27% in some measurements, accompanied by the release of organic compounds that had not previously been detected. Here is where the sequence becomes difficult. Methane is volatile under solar heating. It should escape early. It should not remain hidden beneath outer layers only to emerge after peak heating has already occurred. Yet, the data suggest exactly that, as if methane was trapped beneath a protective crust and only released once that barrier was disrupted. In addition, the ratio between water and carbon dioxide deviates from traditional models of interstellar comet behavior. This is not just about one molecule. It is about timing, proportion, and layered release. The object did not behave like a simple icy fragment gradually sublimating under sunlight. It behaved as though internal stratification was controlling what escaped and when. And that is where the debate escalates. Two broad interpretations have emerged regarding the chemical anomalies. The first is entirely natural, panspermia through passive transfer. In this scenario, microorganisms embedded within rocky ejecta could survive interstellar travel, shielded inside large fragments expelled from planetary systems. If such material were present within 3I/Atlas, then as it releases rocks and dust, it could theoretically disperse microbial material when passing near stars with habitable exoplanets. In this interpretation, 3I/Atlas would function as a biological courier, not designed, not engineered, but acting as a vehicle through natural astrophysical processes. The second scenario is more speculative. It considers the possibility of deliberate seeding by a technological civilization. In that framework, an artificial probe could deposit biological material within or upon an object like 3I/Atlas, effectively transforming it into what has been described as an interstellar gardener. As it travels through stellar neighborhoods, it would disperse microbial life near suitable planetary systems. This interpretation does not claim proof of intelligence. It acknowledges speculation, but it argues that when multiple anomalies converge, unusual geometry, delayed methane release, intense post-perihelion activity, anomalous volatile ratios, intellectual openness is justified. It is important to emphasize, methane alone is not evidence of life. Organic compounds alone are not evidence of design. But when timing, proportion, and structural behavior diverge from expectations, the scientific conversation expands. The question is not whether 3I/Atlas proves life. The question is whether its behavior warrants considering possibilities beyond standard comet models. And if the chemistry unsettled researchers, the nucleus itself would push the conversation even further. As high-resolution data from major space observatories refined our understanding of 3I/Atlas, attention shifted from its tail and chemistry to something far more unsettling, the nucleus itself. Measurements indicate a colossal core approximately 2.6 kilometers in diameter, making it roughly 20,000 times more massive than ʻOumuamua. That alone places it in a different category of interstellar visitor. This is not a small fragment. This is a substantial body that has preserved its structure across billions of years of interstellar travel. But what truly stopped researchers was the internal stratification. The nucleus appears to contain 4 concentric layers. The outermost layer is chaotic, fragmented, and irregular, consistent with what one might expect from an object exposed to cosmic radiation and micrometeorite impacts over vast timescales. Beneath that lies a second layer described as nearly perfectly circular, exhibiting a coherence that contrasts sharply with the exterior. Below that sits a third layer with an irregular dome-like structure, sometimes described as resembling a muffin top in morphology, distinct from both the outer chaos and the circular shell above it. And, at the center, the most intriguing feature, an inner layer exhibiting near-tetranal symmetry. Not random fractures, not amorphous collapse, but geometric organization that appears preserved rather than accidental. Comets are not typically known for geometric coherence in internal layering. They are usually aggregates of ice, dust, and rock held together loosely by gravity and volatile binding. Yet here we see structured differentiation, 4 distinct regimes within a single interstellar object, and the object rotates stably. That stability matters because random rubble tends to wobble. This does not. The outer layer of 3I/Atlas appears unusually resistant. Observations suggest that methane and certain organic compounds were not immediately released during solar heating, but only emerged after deeper disruption, implying the presence of a protective crust or layered shielding. If such stratification exists, then the object's behavior under solar stress becomes more understandable, yet also more complex. It would mean that the outer shell regulates exposure while internal layers respond only after structural compromise. Combine that with the previously observed jet symmetry. 3 emission points separated by 120 degrees, and a new pattern begins to emerge. The jets are not randomly distributed across a loosely bound surface. They appear coordinated with rotational dynamics and structural layering. The rotational period between 7 and 16 hours remains consistent with a stable internal mass distribution. There is no evidence of chaotic tumbling that one might expect from a fractured aggregate. Additionally, the alignment of jets with the sun's rotational axis suggests that emission behavior is not only internally structured, but externally responsive. When you consider a 2.6 kilometers nucleus for concentric differentiated layers, near tetranal internal symmetry, resistant outer crust, stable rotation, coordinated jet geometry, you're no longer looking at a simple icy remnant drifting through space. You are looking at structural coherence preserved over interstellar timescales. And structural coherence invites a question that scientists approach cautiously but cannot ignore. How does something traveling billions of years through deep space maintain this level of internal organization? The mystery deepens, and it may not remain theoretical for long. On March 16, 2026, 3I/Atlas will pass within Jupiter's Hill sphere, the region where the gas giant's gravity can significantly influence passing objects. This is not just another waypoint in its journey. It is a gravitational stress test. If 3I/Atlas is a conventional interstellar comet, Jupiter's immense gravity should perturb its trajectory in predictable ways. Minor deflections, slight changes in velocity, perhaps modest structural shedding if tidal forces interact with a loosely bound body. But this object is not behaving like a loosely bound body. It has shown structural coherence, layered internal differentiation, coordinated jet geometry, stable rotation, a resistant outer crust, a 16 degrees curvature near the sun, large particle ejection without catastrophic fragmentation. Jupiter's gravitational field will now probe all of that. The encounter could compress internal layers, alter rotation rates, or trigger additional material release. It could expose deeper strata if tidal forces exploit existing fractures. It could amplify jet activity. And critically, it provides observational leverage. Spacecraft and telescopes, including Juno, Hubble, and the James Webb Space Telescope, will be positioned to observe changes in real time. This is no longer retrospective analysis. It is live diagnostics. If anomalies intensify, the debate escalates. If behavior remains rigidly structured under gravitational stress, the implications become even sharper. There are three primary outcome scenarios under discussion. The first, and statistically dominant, is mild perturbation, approximately 97% probability. In this case, Jupiter slightly alters the trajectory, perhaps triggers modest shedding, and I/Atlas continues outward on its hyperbolic path. The mystery remains unresolved but bounded within exotic natural explanations. The second scenario, below 3% probability, involves more dramatic gravitational interaction. This could include significant orbital alteration, fragmentation, or enhanced particle release leading to meteor activity within the Jovian system. Such behavior would provide deeper insight into structural cohesion and internal composition. The third scenario sits at the extreme edge of speculation, below 0.001% probability. Yet, it is discussed because the object's velocity of approximately 66 kilometers per second and cumulative anomalies raise difficult questions. This scenario considers the possibility that the object is not purely natural, that it may exhibit behavior inconsistent with passive gravitational physics. Capture dynamics, unexpected maneuvering, or non-gravitational acceleration beyond sublimation effects would radically redefine the conversation. It is important to emphasize, this third scenario is speculative, but it exists in the discourse because convergence of anomalies forces intellectual openness. Jupiter is about to become the referee. If I/Atlas fractures like rubble, the natural model strengthens. If it behaves like a coherent engineered mass under tidal stress, the debate changes permanently. For the first time since its detection, we are approaching an event that could shift this from theoretical anomaly to empirical clarity. March 16th is not just a date. It is a verdict window. For billions of years, I/Atlas traveled in silence between the stars. No sunlight, no telescopes watching, no civilizations measuring its motion. And then it entered our solar system. Since that moment, it has done something rare in modern science. It has forced the world to pause. A 620,000 kilometers anti-tail. 3 perfectly spaced jets at 120 degrees. A rotation that behaves like a lighthouse. Anomalous nickel-to-iron ratios. Delayed methane release after perihelion. For concentric internal layers. Near-tagonal symmetry at its core. Stable rotation under stress. Each detail alone might be explained. Together, they create convergence. And convergence is what stops the scientific community mid-sentence. Because science is comfortable with anomalies. It is not comfortable with patterns. Now, I/Atlas is heading toward Jupiter, toward a gravitational stress test that could expose weakness, trigger fragmentation, alter its rotation, or reveal deeper structural behavior. Telescopes will be watching. Instruments will measure every deviation, every particle release, every rotational change. If it fractures like a loosely bound comet, the mystery contracts. If it maintains structural coherence under Jovian tidal forces, the questions expand. This is no longer just about a visitor from another star. It is about structure preserved across billions of years of interstellar travel. It is about chemistry that doesn't fully behave. It is about geometry that appears organized. And it is about whether all of that can still fit inside conventional models. 3. I/Atlas has not proven life. It has not proven technology. It has not proven design. But it has done something equally powerful. It has forced the door open. And once a door is open in science, it never fully closes again. March 16th is approaching. Jupiter is waiting. And whatever happens next will either simplify this story or redefine it. If you want to follow every development as this interstellar object undergoes its cosmic trial, subscribe and stay with us because 3I/Atlas may have just stopped the world, but the real answer might be only weeks away. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.